Geopolitical conflicts in major energy-producing regions create immediate instability in global supply chains. Because most modern distribution relies on fossil hydrocarbons, any disruption to the flow of oil or gas causes costs to spike across the entire economy. While solar energy offers a path forward, the technology faces a massive storage bottleneck. Photovoltaic cells stop generating electricity at sunset, and the lithium-ion batteries required to bridge the gap at a global scale are too resource-heavy to be a universal solution. To solve this, researchers are developing solar fuels. These are synthetic, storable chemicals, like hydrogen or ammonia, produced by using sunlight to trigger reactions that lock energy into molecular bonds. The challenge is that the catalysts needed for these reactions often require rare or expensive materials. However, a potential solution for building these advanced catalysts exists within our own wastewater. Human urine contains an average of 2% urea. This nitrogen-rich organic compound is a primary precursor for synthesizing the advanced materials needed to harvest sunlight. Repurposing biological waste as a feedstock for energy catalysts provides a way to produce fuel without relying on traditional mineral extraction. This urea-based material is called Polyheptazine Imide, or PHI. It is a class of two-dimensional crystalline polymers that form a stable carbon-nitrogen network. PHI is created through ionothermal synthesis. This involves heating urea inside a bath of molten alkali salts, which act as a high-temperature solvent and guide the molecules as they assemble into a structured lattice. The resulting material is a planar network of heptazine units, rings of carbon and nitrogen, connected by imide bridges. These units form large triangular pores that are wide enough to accommodate metal ions. This specific geometric arrangement gives PHI a band gap of roughly 2.6 to 2.7 electron volts. A band gap is the energy threshold a material must cross to move electrons into a conductive state, and this particular range allows the material to absorb visible light with high efficiency. When light hits the PHI network, it creates excitons, pairs of electrons and positive holes. Because the material is highly crystalline, these charges are quickly separated and moved to the surface of the catalyst to drive chemical reactions. This precise atomic order is what allows a common fertilizer byproduct to function as a high-performance light harvester. Once the charges reach the surface of the PHI, they begin the process of water splitting. The energy from the light harvesting network provides the thermodynamic drive to break the bonds of water molecules. This releases pure hydrogen gas, which serves as a clean, storable fuel. Beyond simple water splitting, PHI possesses a unique property known as dark photocatalysis. This allows it to function effectively as a chemical battery. During periods of sunlight, PHI traps excess electrons in localized distortions of its crystal lattice, called polaron states. These electrons are stored directly within the material's framework. As the material charges, it undergoes a visible physical change. A suspension of potassium-doped PHI will shift from its natural yellow color to a dark blue-green, indicating it is saturated with stored electrons. These stored electrons can remain stable for over 6 hours. When a co-catalyst like platinum is present, the material can continue producing hydrogen gas long after the light source has been removed. This mechanism decouples the production of fuel from the immediate availability of sunlight, allowing for continuous energy generation through the night. The PHI reaction produces two key chemicals, hydrogen gas and ammonia. The hydrogen is used in fuel cells to generate electricity. These cells combine hydrogen with oxygen to produce power, emitting only pure water vapor. The second output, ammonia, has historically been the primary ingredient for global fertilizer production. Ammonia is the essential chemical feedstock for the Bosch-Meiser process, which is the primary industrial standard for synthesizing urea globally. Because industrial urea production is already established at scale, the infrastructure to process these chemicals exists in nearly every industrialized nation. This creates a closed-loop system. The ammonia generated as a byproduct of the solar fuel process can be recycled back into the production of the very urea needed to build more PHI catalysts. For nations with existing fertilizer plants and high volumes of organic waste, this cycle offers a path toward domestic energy production. However, reaching an industrial scale will require overcoming significant hurdles in pathogen management and the economic efficiency of urea separation. The development of polyheptazine imide demonstrates a circular chemical framework where the waste products of energy generation provide the feedstocks for future power.